I know we're a little late already, sorry, I'm running a bit behind. Didn't quite get the camera fully charged, so I don't know if it's going to make it or not, but I think it'll crap out in the second hour, which is okay because I'm going to go over complex numbers. And I might, if I have a little extra time to get ready, I might go over differential equations. So if you guys could, especially today, I had surgery yesterday. I have now a monkey's heart. I had 6 teeth that needed fixing so that they didn't fall out. And the doctor said, well, we'll do one. Most people choose to do one because of the surgery and all. And said, we could do it as 4. You know how hardcore I am? Yeah, 6. Do it. I told the guy, I'll go to prison. I'll go to prison just to make my point. All right, so I had surgery on all 6, and hey, walked out of there, find it kind of numb. And then the numbness wore off. I spent 4 hours last night howling in pain. I had never sweated from pain before, but I did last night. My point being, I'm not so loud, and please be good, all right? Please be very good today. I'm really out of it because of the drugs I took this morning. No, nothing to do with the teeth. Like I said, guys, really just help me out and just be a little bit, I'm just not going to be loud today, and I'm a little slow. So, I have a question.
Were you responsible to know about the complex numbers for the next exam?
No. You're going to be responsible for knowing about complex numbers in 346.
Okay.
Right. So you want to go ahead and, so I've got 2 hours that this material, this battery stuff. I'm going to show you the complex underlines, and I want you to be able to repeat that. But reality is that there's cheats to this, like P1 V1 is P2 V2. There's things like that exist for electrode. And so it's just going to make it easier. You'll know whether you got it right or wrong. And that's incredibly powerful to do, all right? So anyway, so for this next hour, complex numbers, so get used to seeing those. I'm going to show you trigonometry. All those trig proofs you had to know. 2 sine cosine was sine 2x or something. I'm going to show you how to derive all those. It just gets you used to it. The next time we'll go over distributions and averages, and the time after that, I'm not sure, but we'll try differential equations. So anyway, any other questions? We're okay? All right, so that's what we're going to do. Guys, be good. I already hear you talking pretty loudly right over there. So anyway, just go easy on me. I'm already kind of stressed out, so it wasn't fun having these things. I have to go back for more surgery in 2 weeks, too. That's not fun. Okay, so anyway, all right, so we covered batteries last time, and especially my favorite is zinc electrode and a copper electrode. These are the ones you always learn about, and then when I hook it up with a wire, electrons go this way, and I have to have a solution. I think it's SO4, sulfuric acid, I'll have CuSO4 in solution here. So I can see that my copper is going to be plated onto the electrode, and my zinc is going to dissolve. Eventually it completely dissolves and my battery's dead, but then that's just how it is. And, oh God, what else? We talked about the notation, and let me just remind you what that was. And I'm not going to be too crazy about this, so my ox is red, so the oxidation. Oxidation is where the electrons are coming from, and that means that zinc is turning to zinc 2+, that's oxidation, not reacting with oxygen. There's even another couple of definitions for oxidation you learn in grad school, which sucks, but anyway. So if this thing is shedding electrons, the electrons that has to be the source, that makes this the anode. Again, that's the live wire. In other words, if you grab onto this, you grab onto this and you're sitting in a pool of water, you're in trouble. If you grab onto this, of course you're not hooked up to that. If you grab onto this, you're sitting in a pool of water, you're okay. And that makes this the cathode. See, my handwriting is even kind of bad, so I just work with me. Actually, if you get struck by lightning in your car, you're okay, because you're sitting on rubber tires, just don't touch it. Anyway, so my ox is red, so the oxidation's occurring here. Remember, a single line is a phase change, and last time I talked about zinc sulfate, but I'm fine with this too. That means a salt bridge, and then I'm going to have to have Cu2+, and that undergoes a phase change. Remember, this is how you split copper. That same thing. And I don't care about this. I don't even know if I'll put this on the test because I just find it trivial. I don't think there's really any value in knowing this because as soon as you're out here, unless you design batteries, and I don't think any of you are, I mean, I don't know. I mean, it's a good job, but if you're going to end up going to grad school in battery design, especially if you're engineers, I guess you need to know it, but otherwise not. I'm not going to have this on the test. Forget it. Screw it. Another thing I said last time, which was right when we ended, I was a little wrong about this, was we talked about reference states, and the reference state is, where am I at? The reference state is hydrogen. So let me, what you do here is you take H2 gas, and in here it's HCl. So sorry, I hope you don't really need to write over your notes, right? I'm still reviewing. And then this becomes a standard hydrogen electrode. Standard hydrogen electrode. I kind of misspoke. I thought you put two of these together. That was actually wrong. So 1 bar hydrogen, 1 molar HCl, we have 1 molar zinc sulfate. Molarities don't matter for electrodes. And whatever voltage you measure, that's the standard voltage that goes in the table in the back of the book, which is what we're doing now. Let me see, sorry, my notes are a bit screwy here. And so, yeah, here I am. Sorry, I'm a little idiot today. So, what we're going to ultimately, the big picture here is how to use the table in the back of the book to calculate voltages when I throw you cerium and ammonium or something like that. I mean, there's all kinds of different electrochemical reactions I can put in these little vials, and I can make funny little vials to do funny things like use hydrogen as a source of electrons, or use hydrogen as a source of electrons. So there's all kinds of ways I can build these things, and all kinds of reactions I can throw at you with all kinds. Some of them show 2 electrons, some 3, some 1, and you then need to be able to figure this part out, which is oxide, which is being reduced. Then I give you, I'm going to give you delta G, but in a funny way. I'm not going to give you delta G, I'm going to give you the EMF, the electromotive force, the voltage. The voltage is this, for zinc, I'll give you this voltage. And for copper, I put copper in here and I give you that voltage. And that is delta G. So you have to convert to delta G, add them together via Hess's law, and then convert them back to what the actual voltage of the new battery is. So that's the big picture. Taking what you get in the back of the book with your EMFs, converting them to G's, adding them via Hess's law, then converting it back. And I'm telling you, that sounds a little complicated. It's not terrible. It's just a process. It's not nearly as bad as that extended reaction. This is much easier than that. And then there's a cheat on top of that, but I'll explain that last. All right, anyway. So now, where am I at? I should be here. Okay, so to remind you, let me just forget this. This is overview. This is review that the real voltage of the cell. Let's say there's a reaction going on, and we're going to be at STP because I don't feel like complicating things. And as I also mentioned, we have this term, which has the stoichiometry of all the reactants. This would have the stoichiometry of copper sulfate. Copper and zinc don't matter because they're metals. They would have activities of 1, but I need the activity of copper sulfate. I need the activity of zinc sulfate. I can make them 1 molar, which means that they're pretty much 1. And the activities of metals are 1. So this guy doesn't do a hell of a lot. I mean, I've seen other textbooks where they actually throw numbers, for activities, and then you have to tack this term on and figure that out. But I think that if we can just say that the Q is close to 1, which it is, and then just drop it, and then do all the calculations just with this part remaining, then you get the picture. What this would do would mean you have to do more calculator work. And I don't care for that too much. I mean, I test your ability to use a calculator in many ways. I don't care to test it this way. So I'm going to drop that. Okay, so now here's what you get in the table at the back of the book. Okay, so I've said to you zinc and copper, right? And you look at the table in the back of the book, and what you always get are reduction procedures. It's just to make things slightly easier. And this is what you'd see. Now you can find the reduction potential for zinc 1 turning to zinc metal. Zinc solid. I'm sorry, I painted myself into a corner. EMF. Sorry, I hope you can read that again a little louder. 0.76. Minus 0.76 in this case. And then I have CU2 plus, and that's aqueous. See, I'm already forgetting. I should put a little AQ there, but I don't really care. CU solid and 0.68. And these are voltages, which are joules per coulomb. And that's important for more than just that reason. I'll bring that up in a second. Okay, now, here's the thing. All right, we got to start figuring out what to do with this information. And I'm looking at this, and I see that I need to get delta G, right? Because I know I can add delta G via Hess's law. That's actually crucial to know. But I didn't give you that. I gave you this guy here, right? Which is the same if I drop that, whatever. All right, so if I take what I gave you and multiply it by minus the number of electrons, then I've got G divided by Faraday's law. And by F, who cares? All right, let's do this. Minus, and I'm going to, all right, this is EMF still. I'm just shorthanding because I'm just kind of feverish right now. Another thing I need to do, all right? So I can already tell that this guy has a positive delta G. Remember, that's bad. All right, so that's going to not want to happen. So to consider this correctly, I need to reverse it. Because otherwise, I'm talking about a reaction that doesn't want to happen no matter what. Did I put salt? Sorry, see, my head is just not working. Sorry about that. Aqueous, so I'm not going to write it. Again, thanks for working with me. All right, so if I reverse it, then the EMF will change. And now I've got two reactions with negative delta G's, which is good. Now one is going to dominate over the other. And clear up, to figure that out, let me do it the right way. I'm going to multiply this by 2. Multiply that by 2. And that's 1.52. Sorry folks, I made a mistake. This is, sorry, I can't believe I missed out of it. 0.34. And then, okay, this ends up being minus 0.68. I'm not going to worry about this because it's positive. Okay, so again, sorry, my head is a little screwed up. I get the EMFs. I rearrange them so that they're all positive. Positive EMFs are negative delta G's. I then multiply them by the number of electrons, and then I compare the two. Whichever one is, so these are delta G's times Faraday times the F, right? So I then decide which one dominates over the other. Now this one dominates over the other like my two cats. My one cat is actually a bit smaller than the other, but she rules, Juno rules Zoe terribly. Whenever I see those things tearing around the house, it's Zoe running for her life from Juno. So the dominant reaction can force the other reaction to even go uphill because it's just that dominant. Now clearly zinc is dominant. So zinc decides how this battery is going to work, and then copper has to conform to what zinc wants. Now that means I have to balance the electrons. Okay, in this case, I'm done. The electrons cancel. Right, remember, that's why I was bringing up about how battery designs, how we have to have this solid bridge, how they actually have to be connected via high resistance so electrons don't flow, but they need to be connected so that the ions can migrate, because for every negative charge that comes here by the wire, a positive charge of an ion has to go there. Everything has to cancel, and if it doesn't, then charge builds up, and that's the worst battery in the world. So here's the thing. Here's every question, if you haven't looked at your homework already. The first question is, write out the actual reaction. All right, so Hess's law again. So I've gotten half credit already. Well, actually, that would be about, what were they saying? About a third credit. 2 plus copper solid. I'll solid, yeah, solid. I'm not going to care if you write solid or aqueous, that's not important. Okay, this is about a third of the question answer. Okay, so I'm going to say, what's the net reaction, and what's the EMF of the final cell? Now, you know, this is one of those things that if I actually got this wrong, this would not look this way. I know it looks like it's going to come out this way no matter what. No, you can screw this up. It's not hard, but you can screw it up. All right, the next thing is in terms of adding delta G's. Right, so this is Hess's law, and this is now written correctly. And so now I know that I can simply add, like I can just add the delta H's together, I can just add the delta G's together. And so delta G total is going to be the first one plus the second one. Now what I'm going to do is I'm going to leave the Faraday constant. I'm never going to mess with it because it's going to cancel itself out at the end. That's, again, one of the ways that this really isn't that hard. So the first one is, let's do the first one. Now, I didn't have to scale. I didn't have to scale this reaction because the electrons matched. If this guy actually had one electron, I might have to make some adjustments, or if this had one electron, I'd have to make adjustments to that so that the electrons cancel. Again, electrons must cancel. And that's actually part of your homework. So I didn't have to do that, so I have a stoichiometry coefficient that's 1. Because remember, if I multiply a reaction times 2, the delta G should double. Right, so the stoichiometry is 1 times, let me remind you that if we're E0 times the number of electrons, minus is delta reaction. Okay, G naught, whatever, I don't care. Okay, so I have a stoichiometric coefficient. Then I've got the number of electrons, which is 2. Don't forget the minus sign. And then I've got the EMF, 0.34. I'm going to add to that, again, the stoichiometry of the second reaction. I didn't have to scale it. Times minus 2, minus again from Ben Franklin 2, because there's 2 electrons. Times 0.76. Total, I'm kind of sorry folks, I made a mistake, times farads, sorry. So there you go, it's really obvious. The total ends up being 2.2, minus 2.2 volts times farads. And okay, so a volt is a joule per coulomb. Farads are the amount of charge in coulombs for a mole of electrons. So this ends up being a joule. It's minus 2.2. Remember Faraday's constant is like 100 or so. So this 100 kilojoules. So 100 kilojoules. So this is a roughly 200 kilojoule minus 200 kilojoule reaction per mole. So that's pretty downhill. Okay, you've done that part. Now the next thing is to do is to get the voltage of the cell. And so to do that, I'm going to get what I just calculated and divide by the number of electrons divided by Faraday's constant, and that ends up being minus 2.2 volts-farads over 2 electrons times a farad. And this ends up being 1.1 volt. So there you go. And now you've answered the question, you're done. Okay, now let me point out something here. All right, for one, on the test, I want to see you do that. Let me just be perfectly blunt, that's on the test. Probably maybe more than one question, no more than 2. So you show me that you understand that this information needs to be translated to delta G's. Delta G's add via Hess's law, via the first law of thermodynamics, and then you go backward. Now, and yeah, it's a bit complicated, but there's a trick. Here's the trick. Once I got this guy turned around, and I saw that it was dominant, all I had to do was add the results here. 0, 10, 11, 1.1, 1.1 volt, same thing. Right, okay, so again, the trick is, no matter what, figuring out which one is dominant, making the other one conform, and notice that I didn't mess with the scaled versions, I just took the EMFs and added them. Now, again, this is a bit of a pain in the ass. Let's say I did have, and I'm going to just do nothing but examples for the rest of the day. Even if I had to scale one of these, I still just add the EMFs together. In other words, it's shockingly easy to do this just by figuring out which one goes which way. You may have to add a minus sign, that happened here, but at the end of the day, you just add them together. And on the question, I'd asked you to do this, and now you have a way of double checking yourself. So anyway, a bunch of examples, and I'm going to show you again and again about 5 examples of how to do this, and then we're going to double check. Question?
Actually got 2. One of them, when you actually, let's say if you want to scale one of the equations, let's say you have to multiply by 2, would you actually multiply the EMFs by 2 as well?
No, not this column. No, not this column. Here, not even here. This is just, right, I scale only by number of electrons. And then that allows me to figure out which one's dominant, and then I figure out, and once I know which one's dominant, then I take care of the stoichiometry. Now, the stoichiometry, in terms of, what if you had to multiply 1 by 2, which I'm going to do an example right in 1 second, that comes right here. That's where that's going to happen. Let me work some examples. You had another question?
Yeah, actually about the ones, what are they again?
The stoichiometry, what you just asked, the stoichiometry. I'll write that out. I'm just working the board terribly today.
It's
So.
actually the stoichiometry of, which ones again, is it the electrons or no?
So stoichiometry minus number of electrons. That's this part, and then the EMF. So the scale you just asked about, minus number of electrons, a minus sign because of Ben Franklin, and EMF. And Faraday's constant. I'm not. If I ask this and you forget F to write F, I'll take off the point. So 9 out of 10, pretty good. And you saw why I didn't bother to actually include it, because I'm going to divide it out the end, and that happens every time. So you never have to complicate it. So anyway, now for the rest of our time, I know I don't do this very often, but it needs to be done this time. Let me just do a bunch of examples, because your homework is it's basically 8 questions just like this. And I make them kind of clever, and I'll help you out with one of them is kind of interesting. Okay, so on the test, I'm going to say, solve the net reaction and give me the final voltage for a battery constructed of this. Okay, this is cerium, 4 plus an electron, goes to cerium, 3 plus. God damn it, I did it again. I did myself one for and this is 1.61. These are in volts. Okay. And again, remember this is actually delta G. And what I'm going to do is say, okay, that's connected up to copper. So you see here, I've already set us up. We have a stoichiometry problem. So anyway, and look at this. You can actually have. It looks like I don't even have an electrode. So whatever wire I use to connect the 2 sides of the battery, that wire actually will just dip into solution because these were made aqueous. That's a detail that will never come up again. Minus 0.34. Okay, now the trick is, let's multiply these by, the first thing to do is, no matter what, I'm automatically going to switch this one. Because it's negative, that's a positive delta G. So I may, so if I'm going to figure out which one's dominant and I have the wrong side, I'm going to completely screw this up. So I automatically, no matter what, flip them. And now let's figure out which one's dominant. Okay, this guy is fine as it is. And this guy is going to get a boost. Minus. And cerium wins. Okay, so cerium is large and in charge. Let me make sure I get this right before I tell you something that's wrong. Okay, so again, Cerium has the most negative delta G. Now, I told you that the winner is going to force the loser to do what it wants. In this case, cerium is going to force this guy to turn itself around and work in reverse. And I've already written that out, so that's kind of good. So question?
For that second one, where copper 2 electrons plus 2 electrons, isn't that supposed to be a positive 0.34, and then it becomes negative when you flip it?
Oh, Jesus, what am I doing? Yeah, I just added a minus. Did I just add a minus sign? Yeah, positive, negative over here.
Right, okay.
Sorry, yeah. I don't know what's wrong with me. I actually got it in my sleep. So that's what, what the hell is wrong with me? No, wait, no, I ignored it, sorry, I ignored this one because it was wrong. I did it right here. What the hell? I feel really stupid right now.
It's positive and then it's negative, and then it multiplied by the 2, then, yeah.
Oh, wow, worst day ever. Before with my notes, I can say, yeah, I'm jumping ahead, that's the problem, sorry about that. Okay, thank you for pointing that out, I'm just really out of the book, so thanks for being quiet and working with me. So, sorry if I'm ruining your notes. So again, this guy, so I actually engineered the homework, by the way, where like one of the reactions has a ton of electrons, more than the other, but still ends up being the loser. So that's why it's towards one of the last ones. So just because this guy, one of these has a lot of electrons, normally it makes it the winner, but not always. And here's an example of that. That's why I'm doing this one. And again, because this is the winner, this guy has to turn itself around, and then I need to change the stoichiometry. Okay, so the first thing to do is, since this is the loser, it's the one that has to it has to reverse itself. Now, so in other words, this guy is going to go not downhill in energy, up, because something else is pushing it further. So the first thing to do then is knowing that the electron is, that this is the winner, and the electron's on the left, and this one has to have the electron on the right. That's probably why I'm getting so confused, because I already know the answer. Okay, so now this part, what I'm doing now is I'm trying to get the net reaction. That'll be, again, 1/3 of the credit. Okay, now, again, I had to flip this guy because it's the loser, and I also started with this one. Why did I start with this one? Because it has the dominant number of electrons, even though it's the loser. And so now I'm going to make cerium conform to that, and I see that I have to double. If you're having trouble seeing it, I see that I have to double everything. Okay? And notice I'm not worried about EMFs. I'm not doing that right now. Okay, and then the net reaction is copper solid plus 2 cerium atoms in solution of 4+, go to copper ions in solution plus 2 cerium 3+. Okay, so there you go. That is again, this again is 1/3 the points. All right, now for the harder part, EMFs. So, let's do delta G, delta G1, delta G2. Okay, let's do, what do I want to do here? Let me rewrite these. Let me rewrite these here. So this is reverse 1.34, and this guy is normal. Notice that I did not, so all I did was, since I had to reverse this reaction, I had to put a minus sign. That's the only rule. Flip the reaction, the battery is negative. Now notice that I had to multiply this by 2, but I did not multiply the voltage. All right, now here's the thing. Again, what is a volt? Is a joule per coulomb. Joules are intensive, extensive. Extensive, right? Joules are extensive, it's energy. Coulombs, extensive, intensive.
Intensive.
Extensive. it's charge. You can have more charge. Like if I pet my kitty cats and they get all staticky, then they rip my face off. That doesn't have anything to do with anything, does it? But anyway, so voltage being a joule per coulomb, extensive over extensive is right. So if I multiply this by 2, I don't do anything. And by the way, that's correct. Don't do anything. Just write them out. Okay, now, again, I'll start with this one. I want to do a stoichiometry of 1. I didn't have to scale it. All right. I don't scale these, but that's because they're intensive. G's are extensive. I do need to multiply those. I do need to do the Hess law scale. Okay, times minus number of electrons, minus 2. And I'll point out what all these are. Times the EMF, negative 0.34. That's a volt, and I multiply by a farad. Plus, all right, let's do stoichiometry, and that, okay, now we have a stoichiometric coefficient, minus number of electrons. Okay, now, so don't get confused with this. This is actually a 1 electron minus number of electrons. It's still minus 1. Oh, but there's 2 electrons there. Oh, yeah, I took care of that here. So don't do it twice. You see what I mean? I know this gets a little bit hairy, but again, when I scaled this by 2, that took care of it, leaving behind the fact that it really was just a 1 electron reaction to begin with. That's the only thing you're going to ever screw up when it comes to calculating this. So don't mess it up. And again, okay, the voltage is 1.1 volts times a farad. Okay, and the result is, what is the result? I don't really notice. 4. Minus 5.4. You double check with your calculator. Volts times farads. Okay, now you've got 2/3 credit. Now the EMF of the new cell is again right up there. This is going to be minus 2.54. Volts farads. There's a minus sign in front. I divide the fact that this is a 2 electron thing, and that I get from here, and I divide by a Faraday's constant, and that is minus plus 1.27 volts. And that's the answer. So, minus that, let's see, 4 minus 1 is 7. 6, 3, carry, do you want to carry, now it's going to be a full, right, carry 1, and 7, 2, let me do it 1 by 2, 1.27. 1, 2, 7, 4, 3, 6, and 1 and 1, right, okay, there we go. So again, show me you know what the heck you're doing, and then do this last step, but double check yourself and get it right every single time. How about another one? Let's do another one, let's do a harder one. And so that this isn't so blindingly boring, I'm going to do one that's really important in terms of energy, and I'm going to point out a bunch of things about alternative energy with this reaction, so that this isn't completely boring beyond belief. And I told you after today's lecture, we're going to go through, what are we doing? Phase diagrams. When we do phase diagrams, I only ask you to do one thing. Bring a stick to tilt your head up, because it's going to be that boring, right? Maybe, we can just cancel class, right? No, not going to cancel class. Like to cancel class. So let me, sorry. I did 2 steps ahead in my notes, and I don't want to make it that easy. 4H plus 4 electrons goes to H2O. Let me put the standard. You usually see it like a little curly thing here. 1, 2, 3. 2H plus H2. Actually, you should know what this is. What is it? Right, standard hydrogen electrode. Okay. So, again, how about I just put it up here? I'm just going to go ahead and put it there. Now, so now this one's kind of easy because remember that voltages want to be positive. And note that our final voltages in the two examples I already gave, they're always positive. That's 99% of the time. On one of your homeworks, I'm warning you, and I've already look at the homework, there's one that says, hint, hint, this is going to be weird. You can build batteries with negative voltages. I double checked on the internet, which is never wrong. And it is true. So one combination, this will really be testing you whether you know what you're doing. One of your combinations does turn out negative. Just want to point that out. This is an easy case because I don't have to flip anything. Well, I am going to have to flip this. So let me rewrite this. Now, again, the question is asking what is the net reaction. This is clearly this is that, this is that. We didn't have to scale anything. So I know that the net reaction is O2, 4H plus 4 electrons. Okay, and then this guy, now again, since this is a winner, this has to conform because it has to cancel the electrons. So this is going to take H2 goes to, I have to scale. Unfortunately, the stoichiometry isn't going to matter in this case because it's 0. It's going to make 4 electrons. 4 electrons will be plus 4H plus. And the net total, again, the only thing that should cancel are electrons, O2 plus 4H plus. No, I'm sorry, I'm an idiot. Yeah, I knew something was wrong. Plus 2H2O, 2H2, it would form 2H2O. Okay. And let's do the delta G's on this. And then obviously I'm going to tell you a little bit about energy production and why, when I was your age, I was wondering why we didn't do more with solar cells, and I'm going to actually explain a major limitation of solar cells here in a second. So I know this is still boring beyond belief, but just work with me. Delta G2, going to make that 0. All right, so this ends up being stoichiometry. I didn't have to scale the dominant reaction. And minus 4 electrons times 1.23 volts. And that is obviously, I've already done it, minus 4.92 times farads. And therefore, the E of the cell is minus 4.92 volt farads. Don't forget the minus sign, 4 electrons times Faraday's constant, 1.23 volts. Since I didn't have to do anything, I didn't have to reverse anything because this is 0, minus 0 is 0, 1.23 volts when I add them, 1.23, works just fine, all right? So do a couple more examples. Question?
Why isn't your V in that column negative?
Why is what here?
The new, right next to your voltage column on the left.
Yeah, normally I make it minus, right? Normally I make it minus. Yeah, so I normally I put a minus sign to remind myself that delta G's are downhill. If I'm being fast, as I'm doing today because I'm a little out of it, sometimes I forget them and then I look for the bigger number. Right, you just know how it works, and even if you screw up, you won't screw up. Right. My way is slow and methodical, but it always works, right? And you have 2 hours for the test, you're going to be fine. Okay, now I want to point out one thing, that if you want to drive this in reverse, there's a couple of things. Let's take H2O and make oxygen plus hydrogen. Well, there's a few things. For one, this guy here, this 1.23 volts, did any of you know, ever heard of using this for power? This reaction? You've heard of this before? What's it called? A what? I already forgot to.
Called rocket fuel.
A what?
Rocket fuel.
No, that's actually hydrogen, by the way. People think it's this, they're actually not telling the truth. That's actually hydrogen. It's been since von Braun's time. This is a, oh God, what the hell? Okay, none of you remember this? It's a type of battery that, again, uses actually oxygen and hydrogen.
What, hydrogen fuel cell?
A fuel cell, it's a fuel cell. Oh, thank God. I just can't stand it when a word's in the back of my head. I can't remember it. This is the source of
I
fuel
know, but
cells.
I said it.
And that's actually how, this is what they had on the space shuttle while the space shuttles were flying. This was actually where they got their electrical power. Remember, that thing didn't have solar panels. Now, you may think that this looks kind of dangerous because hydrogen and oxygen is obviously going to make boom. However, you already strapped your ass to a rocket. How much worse can it get? Right? That, and actually, this is one of the best battery sources that exists. We don't put them in cars, again, because of the big boom part, so, because people drive like asses. All right, so a great way to get power, if it can be done safely. So why don't we take water, use solar light to split it, collect the hydrogen and oxygen, and then go back and we get the energy out in the form of electrons. Why don't we do that? For one, let me point out that, sorry, let me see, I have the numbers. Energy is actually going to be number of electrons minus number of electrons times Faraday's constant, and times the EMF times Faraday's constant. That ends up being 4 times minus 4 times 1.23 volts times 96.485 times 10 to the third power, and this ends up being minus 475. Sorry, I did this for the forward reaction. So if I did this for the backward reaction, it's positive. Okay, so my point here is that splitting water is kilojoules. I'm an idiot. Now, in your sense of scale, how big is that? Yes, it's absolutely gigantic. It's horrifically gigantic. What kind of kid was mine? And the reason is, this is actually kind of horrible. It's because this thing has only one, the molecule of water has one oxygen, but oxygen comes in the form of 2. That means that you have to not shuttle 2 electrons. You don't have to shuttle 2 electrons to get oxygen to split into water. You have to do 4 electrons. Because that's, again, because of the disconnect between water having one oxygen and oxygen coming in the form of 2. It actually ends up doubling your problem. And the energy you need scales with the number of electrons. And as you're going to learn in kinetics, the speed at which something happens is e to that number. Meaning that this is the most horrifically uphill reaction that exists. So the voltage necessary, of course, is still plus 1.23 volts. And the problem is silicon solar cell is 0.6 volts. So in other words, to get our hydrogen and oxygen, see, this is what I thought when I was a kid. Why not get a solar cell and stick it in a bucket of seawater and wait for the hydrogen and oxygen to come out and just collect it? Even though it's slow, you just have to wait, and eventually you collect enough hydrogen and oxygen. Because electricity in water generates hydrogen and oxygen. That's something you saw in elementary school. The answer is, it's not true. It won't generate anything. It just sits there wasting time. The current doesn't go anywhere. Actually, the solar cell gets charged and it just doesn't do anything anymore at all. So you could wait forever. And because of the solar cell of silicon being what it is, it never generates a single molecule of hydrogen. And that's the major problem with solar power. is exactly this. So you may think, well, make a solar cell with a higher voltage. All right, now here's some semiconductor physics for you. The band gap of silicon in energy units translated to voltage is 0.6. It depends on the band gap. Now silicon is a black color. That means it absorbs all the solar light. Now if you had a semiconductor that had this kind of band gap, it actually doesn't absorb much sunlight at all because it's a wider band gap. Wider band gap means higher energy, means higher voltage, so much voltage that it doesn't absorb solar light. Major problem. The way that we actually do this is you take, remember how you take one battery and you can connect it to another battery and you can connect it to another battery and the voltages add up? Right? You can do that. You can do it with solar cells. You take different types of solar cells, you need a minimum of 3, and then you can do a little bit better than 1.23. And then you can split water. Now, anyone can guess what the problem with that is? Yeah, money. That is the most expensive damn thing that exists. They're horrifically expensive, and we need to technically coat Arizona to get all the world's power, and we can't remotely afford to do it. So, don't have kids. They're screwed. Mad Max? That's it. I told you. That's not a movie. That's a documentary from the future. So anyway, I think I had 1 or 2 more examples, but screw it. I think you get the point. Break for an hour and 10 minutes. I think I should check my temperature. In all honesty, I think I do have a fever. 10-minute break, and then you don't have to stick around, all right? But you're all gonna.